product page reads its price from a cache. If the key is missing, the application loads the price from the database and stores it in the cache. This is cache aside, and it works well until the price changes. One common write path updates the database and then deletes the cache key. The next reader misses and reloads the new value. The dangerous part is the word then. The database update can succeed while the cache delete fails.
Now the database says $20 and the cache still says $15. A time to live eventually removes the stale value, but until then the customer sees the wrong price. Reversing the order does not eliminate races.
If the writer deletes the cache first, a reader can load the old database value before the update commits and write that old value back into the cache after the database changes. This is why cache invalidation is a coordination problem, not just a delete call. The correct strategy depends on how stale the data may be and how writes occur. For data that can tolerate a short delay, use a bounded time to live and accept the defined staleness window. Add jitter so millions of keys do not expire at the same second. For stronger freshness, publish a durable change event after the database commit and have consumers invalidate or refresh affected keys. The event must survive process crashes, which is why systems use patterns such as an outbox record written in the same database transaction as the business change. A separate worker publishes the outbox event. Versioned keys provide another tool. Instead of overwriting product price, write product price version 42 and update a small pointer or include the version in the object. Old writers cannot replace the new version if readers verify it. This costs more space and lifecycle management. Writing the new value directly into cache can reduce misses, but it creates two writes that must agree and may still lose order when concurrent updates arrive. Treat the database or another declared store as the source of truth. The cache is a derived copy. Read paths need stampede protection too. When a popular key expires, thousands of requests may all query the database. A short per key lock, single flight request coalescing, stale while revalidate, or background refresh can allow one request to rebuild while others reuse a controlled stale value. Observe the system. Measure hit rate, load latency, stale read incidents, invalidation failures, event lag, and fallback load. Test the exact race by pausing between database commit and cache deletion. The cache strategy is correct only relative to a freshness requirement. A newsfeed can tolerate seconds. A permission revocation or price charged at checkout may require a direct authoritative read or stronger coordination. Senior design starts by naming the allowed staleness, then selecting the simplest mechanism that keeps every race inside that boundary.